Modern medicine increasingly centers on cellular senescence. When a cell stops dividing but refuses to die, it remains in the tissue, fundamentally altering the environment by emitting a continuous, destabilizing wave of biochemical signals. We usually view aging as a collection of independent failures. A lung loses elasticity, a joint develops inflammation. But these symptoms often point toward a more unified problem, a systemic stall where cells enter a specific stage of their life cycle and lose the capacity to move forward. This stall manifests as the senescence-associated secretory phenotype, or SASP. It is a persistent broadcast of cytokines and proteases. Because the cell can no longer resolve its own internal damage, it forces its neighbors into a state of chronic, unresolved alert. Biologists define this as the non-returning state. The cell remains metabolically active and structurally present, yet it has exited the productive cycle of repair and division that keeps a tissue healthy. Senescence represents a specific topological failure mode, a geometric stall where a biological system attempts to complete its operational circuit but lacks the momentum to return to the start. We typically describe the immune system as an army defending a border. This metaphor of warfare is useful for infection, but fails to explain the structural persistence required for an organism to survive decades of internal stress. Immunity is a recursive closure engine maintaining boundary integrity through a self-referential loop governed by a specific ratio. The numerator tracks formative pressure, recruitment velocity, and signaling cascades. The denominator tracks containing density, structural matrix strength, and stabilization frequency. When this ratio reaches unity, the system is phase-matched. The force used to initiate a response is perfectly balanced by the force used to stabilize the tissue afterward, allowing the system to persist. These dynamics play out across a 9-fold lattice. In this watercolor model, we see how the system moves from initiation into modulation and eventually toward stabilization, following the golden arrows through a complete cycle. This suggests that biological persistence relies on an autopoietic loop. If the response to a perturbation can complete this circuit and return to its starting state, the system maintains its integrity. We can map the specific actors of innate immunity onto this lattice. Each cell type fills an immutable phase role, working together to traverse the grid. The operational sequence follows a backward S path. It begins in the formative arc, moving from left to right across the top row to generate initial momentum. At address 1, the neutrophil acts as the centrifugal spark. It provides the pure outward force needed to convert potential into an active response within hours of an injury. Moving to address 2, the dendritic cell functions as the exploratory scaffold. It captures the details of the threat and organizes them into coherent pathways for the rest of the system to interpret. Address 3 is the mast cell, the diffusive crust. It floods the local field with histamine and cytokines, ensuring the entire tissue environment is saturated with the activation signal. A failure at address 1 manifests as chronic netosis. The initial spark refuses to extinguish, causing hyperinflammation as neutrophils discharge oxidative bursts and traps. This formative arc creates massive, undeniable momentum. If the system cannot redirect this energy inward, the resulting inflammation becomes lethal to the host. The traversal then drops to the middle row, moving backward from right to left through the field of modulation. Address 4 is the macrophage, acting as the torque hinge.
This is where the M1 to M2 transition occurs, physically pivoting the system from expansion toward integration and repair. In chronic disease, this hinge can lock. We see this in immune exhaustion, where epigenetic changes paralyze the cell, causing it to oscillate at this pivot point without ever completing the turn toward resolution. At address 5, the fibroblast acts as the coherence anchor. It maintains the extracellular matrix and defines the physical boundaries of the tissue, serving as a dynamic still point for the system. Fibrosis occurs when this anchor point rigidifies. The fibroblast becomes a pathological scaffold, replacing functional tissue with disorganized, stiff scarring that prevents any further renewal. At address 6, the eosinophil manages the focused indraw. It collapses the wide, diffuse signals of the earlier phases into precise corrective actions tailored to the specific tissue. This torsional pivot is the critical moment of decision. The system must successfully turn here to transform destructive energy into stable structural memory. Finally, the traversal drops to the bottom row, tracing left to right toward the completion of the cycle. Address 7 is the monocyte, representing deep compression. It holds biological potential in a latent quiescent state, ready to differentiate whenever the cycle begins anew. Address 8 is the basophil, or gestation saturation. It continuously primes the field, ensuring the tissue is conditioned and ready for future encounters. Address 9 is the natural killer cell, the centripetal surge. It aggressively enforces the organism's identity by clearing out cells that have failed to complete their own internal closure. Cancer relies on corrupting this grammar. By downregulating surface markers, tumor cells hide from address 9, ensuring the centripetal surge never clears them. For the organism to return to health, the containing arc must remove these altered states, resetting the field so the next cycle can begin with a clean slate. We can now re-examine the systemic danger of senescence through the lens of this phase grammar. In a senescent cell, the coherence ratio collapses. The formative engine fails, but containment remains locked. Topologically, the wave reaches address 9, but lacks momentum to jump back to address 1. It pools, stalls, and cannot re-enter the loop. The SASP broadcast represents a specific failure, a stalled diffusive crest signal from address 3, emitted by a cell paralyzed in the containing arc. It continues to broadcast activation even though it can no longer move. Senescence represents a system permanently locked open. It transmits a continuous signal of distress without the mechanical capacity to complete the circuit. This creates immunosenescence. The accumulating signals from non-returning cells damage the lattice itself, degrading the immune system's ability to interpret and resolve new threats. Standard treatments often focus on suppressing the immune response, which can break the lattice entirely. A more precise goal is the restoration of the conditions that allow the traversal to complete. Senolytic therapies act as artificial address 9 supplementation. By forcing the removal of stalled cells, they enable the tissue grammar to force the circuit closed. This continuous flow is the ideal state of autopoiesis, a balanced, unobstructed movement of biological data through all 9 phases. Understanding disease as a stall in the grammar of closure changes our objective. If absolute health is the dynamic completion of this circuit, then our target is the removal of the stall itself. For a biological system to persist, the